The last section of chapter 3 is one of my favorites. Of course, they're all my favorites, but still, that is the truth. That 3.8 is one of my favorites. Related rates. So as I mentioned earlier, if you had a really good time with optimization, the good times are going to continue to roll right into related rates. First of all, why the title, Related Rates? Well, of course, we've been studying the derivative most of the first semester, and the derivative is related to the rates how. What is the derivative? It's the slope of a tangent line. That's the Leibnizian perspective. It's the rate of change at what? On an interval or at a time? At a time. So it's the instantaneous rate of change. So we're going to be using calculus here to find instantaneous rates of change of aunts and uncles and brothers and sisters. That's why we use the word related. Okay? Not really. We are going to be looking at the rate of change of rates that are related to each other in a closed system. So I always like to start with an example of we are blowing up a purple balloon by inserting TNT into it and lighting the fuse. Not that kind of blow up. We are inflating a balloon. Okay? We are inflating a balloon. What then regarding that balloon changes as it inflates? The volume, right? Let me finish coloring my purple balloon while y'all are thinking. Yeah, so the volume, what's the volume doing if we're inflating it? Increasing or decreasing? Increasing. The volume is increasing. And that's about it, right? No, what else? The surface area is what? Increasing. What else? The mass? What's happening to the mass? It's increasing, yeah. What else? How about the radius? Oh, the fun. The radius is increasing. What about the diameter? It's also increasing. What about the, the girth? It's kind of like the diameter. It's increasing. The thickness of the balloon. The thickness of the balloon is decreasing. I was going to ask, is anything decreasing? Yeah, the thickness is decreasing. What about the opacity? Also decreasing, right? Also decreasing. As you stretch it, it becomes more transparent. What about the tension? Oh, it's increasing, right? The tension because you're tense. You don't know if it's going to pop or not pop. Because as you become tense, questioning that, the balloon itself comes under more tension. Yeah, so anyway, all of those are changing. Hi. Thank you. All of these things are changing in this one little simple system, but they're not changing at random rates, right? Or unrelated rates. They are all changing at rates that are what to each other? Related to each other. And that's what related rates are. We're going to be looking at all kinds of wonderful word problems, and we're going to be looking to see at any given moment in time how fast any one of these quantities or others are changing instantaneously. Okay? Cool. So what makes this section unique is that we're going to be taking the derivative of a quantity with respect to t, where t is time. The ultimate independent variable is time. Okay, so time is always going to be our independent variable. The thing, though, is we're not going to have the variable t in any of our equations usually. Most of the time we don't. So we're going to be taking the derivative how? Implicitly, right? We're going to be taking the derivative implicitly. So in a sense, these become more like physics examples, okay? How fast something changes with respect to time. So we're going to start off by interpreting an English sentence and writing it as a mathematical sentence, because that's the first key to unlocking related rate problems. You have to read it, know it's a related rate problem, and then you have to assign values to certain things, okay? So the first one is, in English, Mortimer is growing at a rate of 3 inches per year. All right, so a couple of clarifications here. Mortimer is the name of this individual. And when we say he's growing, we can mean like his belly's getting bigger or his nose is growing like Pinocchio. But typically, we agree on height. So is there anyone objecting to when we say he's growing, his height is increasing? Is that okay? All right, good. So Mortimer's height is increasing. So now he's growing at a rate of 3 inches per year. So how do you know that that's a rate, first of all? Because what? Okay, inches per what? Per year. Okay, so if you have a quantity per time, that's a rate of change with respect to time. So what is that immediately affecting? If we agree that it's his height, we could say the height, right? And we can use h for height. So what you're going to do is you're going to transcribe the rate that's given in an English sentence into a mathematical model. Now, we are going to use Leibniz notation pretty much exclusively here. So this gives us the rate of change of height with respect to time, which we are going to write as dh dt. Okay, that's a rate of change of height with respect to time. We then, and probably the most important thing, we have to assign that rate the correct sign, S-I-G-N. It's either going to be positive if that quantity is increasing or negative if that quantity is decreasing. And you have to tell from the verbal description, is this going to be a positive or a negative 3? It's a positive 3 because his height is increasing. How do we know his height is increasing? It's growing. Yeah, so the English sentences aren't always just going to be straightforward. The height is increasing, the height is decreasing. They're going to use like vocabulary words like growing or passing or something. And you're going to have to interpret that as quantity increasing or quantity decreasing. If the quantity is increasing, it's going to be a positive rate. If the quantity, though, is decreasing, it's going to be a negative rate. And if you don't assign that value a negative number, it could throw off all the rest of the calculation. So that's why we're starting with this, because it's the most important part. Okay, part B. My stock portfolio is losing 5 cents each and every day. Yikes. Okay, I'm going to go broke here after 20 days. I only had $1 in there. All right, let's see. So what's actually changing here? The stock, the number of stocks I have, or the value of the stocks? The value, yeah. So you can make up your own variables, and that's going to be similar to what it was in optimization. You get to introduce your own variables. So I'll use V for value, the value of my portfolio, okay? So now, here's the key word, losing. That's how we know it's changing, 5 cents per day. So I'm going to call that dV dt, the rate of change of the value with respect to time. Is it going to be positive or negative? This one's negative, okay? And depending on what units you want to use, you can either say 5 cents per day, and we write the cents unit after the number, or you could say negative what if you wanted to use dollars? Yeah, 0.05 per day. And for dollars, we typically put it in the front. So whatever you want to do, you got to make sure that the units are clearly defined. There could be some conversions to do, right? So either 5 cents a day negative or negative 0.05. The next one, the radius of a circle gets larger by 4 feet every hour. So what's changing? The radius. And the radius is increasing or decreasing? Increasing, right? The word larger implies it's increasing. So I'm going to use little r for radius. It's kind of intuitive. So getting bigger by 4 feet per hour is going to be dr dt. That's units of radius per units of time. Is it positive or negative, the rate? Positive, good. And it's 4 feet per hour. And then the last one, the outside temperature is dropping by 5 degrees Fahrenheit per minute. All right, so what letter do you want to use for temperature? Capital T. So since this is a rate of change of temperature, we're going to label that as dt dt. And I'm glad y'all said capital, right? Because otherwise they would divide out. So dt dt, as long as they're different, that's fine. Is it going to be a negative or a positive rate? It's a negative rate because the key word is dropping. Temperature is decreasing by 5 degrees Fahrenheit per minute. All right, so in that little activity, we had 2 that were positive, 2 that were negative. But we now know how to write a verbal rate of change with respect to time as a mathematical rate in Leibniz notation. All right, so let's kind of put our toe in the water and see what the temperature is. The length of a rectangle is decreasing by 2 inches per second, while the width is increasing at 3 inches per second. Oh, there's a lot going on with that rectangle. Whew. When the length is 10 inches and the width is 6 inches, how fast is A, the perimeter changing, and B, how fast is the area changing? All right, so first of all, how do you know this is a related rate question? Yeah, it's inches per second, as you said, or change per time. That's the key. When it's change per time, whether it's per second, per hour, per day, that is going to be related rate. Okay, how do we know it's a calculus problem versus an algebra problem? How do we know it's instantaneous instead of average rate of change? Yeah, the key word is when. That's referencing a moment in time. And instead of saying like when t equals 5 minutes or seconds or 3 seconds after it started, we're not going to be referencing the moment in time by referencing time at all necessarily. Rather, we're going to reference a moment in time by a current size of the quantity. So it says when the length is 10, and similarly when the width is 6. So at that moment, so it's like you bought a ticket to the 50-yard line to watch that rectangle change, yeah? And you brought your high-speed camera with you. And then right there, when the length was 10 and the width was 6, right in the middle of them changing, you snapped a photo. And you captured that moment for posterity. Then you could take that photo back to your math lab, right, and do calculations. So the other main part of a related rate problem is in recognizing the moment in time. Okay, and so because it's like you took a picture, I always draw it in a camera. It makes them kind of fun. So when the length is 10, I'm going to use L for lengths. And when the width is 6, I'm going to use W for width. So those are my moments in time. I'm going to put that in an old school camera with a flash cube. All right, old school camera. If you want to put them like in an iPhone camera, that's entirely up to you. If you don't even want to put them in a camera, that's fine. But that is the snapshot moment. That's what I call the snapshot moment. We took the picture right there. So that makes it instantaneous. That makes it a calculus problem. Now, just like with optimizations, if a diagram will help you further understand the problem, you should sketch a diagram. We're talking about a rectangle changing. So I'm going to go ahead and draw a rectangle. And I have already chosen the variables to use, L and W. It could be anything, really. So now I've labeled the diagram. So once you do that and you define your variables in the diagram, now you want to start transcribing things. You've identified your snapshot moment. Now recognize any rates that are given verbally as mathematical quantities. What do we know? The rectangle is decreasing, the length is decreasing by 2 inches per second. So just like what we just did, the length of the rectangle changing is going to be dl dt. And is it going to be a positive 2 or a negative 2? Negative 2. It flat out says here that it's decreasing, while the rate of change of the width with respect to time is dw dt. And that one, it said the width is increasing by 3. So is that positive or negative 3? Positive 3. So what you're doing is you're just making sense of the problem. You're assigning variables to your unknowns. You're identifying the snapshot moment, which really only has to reference one of those two. And then you're transcribing your verbal rates to mathematical rates, quantities, with plus or minus signs. All right, so now we go to part A. At this snapshot moment, how fast is the perimeter changing? So I always like to give ourselves a target. If you don't know what you're aiming for, it's kind of hard to hit the target. Or if you don't know where you're going, any road will get you there. We're trying to find the rate of change of the perimeter with respect to time. So I'm going to use, guess what letter for perimeter? I'll use P, yeah. So dP dt is our target. That's what we're looking for, the rate of change of perimeter with respect to time. Now, here's ultimately why it's called related rates. I have two rates of change over here for the length and width. I want to find the rate of change of the perimeter. I want to be able to relate the rate of change of P to the rate of change of L and or W. I need to relate these rates to each other. That's the task. Okay? So before you can relate the rates to each other, you have to relate the quantities to each other. So I'll write that out here. We must first relate the quantities before we relate the rates. All right, so here we go. In a rectangle, the quantities are perimeter, length, and width. Man, does anyone know how we can relate the perimeter to the length and width of a rectangle? P equals 2L plus 2W. Brilliant. I like that. So this is kind of like what we did in optimization. We had to write our own equation. We just wrote our own equation right there. But we're not trying to optimize that. So having the perimeter as a function of both L and W is both fine and dandy. It doesn't have to be in terms of a single variable. You can leave it like that. There is no restraint or constraint equation to write. We want to know then how fast that changes. So this would be like if you're looking at particle motion, this would be quote unquote analogous to the position equation. Okay, if you know the L and you know the W, you can find the position or the value, the instantaneous value of the perimeter. If you know the perimeter and the length, you can find the instantaneous value or position of the width. We want the rate equation. So guess what we're going to do to go from the position to the rate equation or the velocity equation? The derivative, yeah. Except we're going to take the derivative not with respect to P, not with respect to L, not with respect to W, but with respect to T. So to show that, remember, we put d dt colon. That signals your intention here. You're telling me the verb ddt, you're taking the derivative of what's above. All right, so what's the derivative of P with respect to T? dp dt, right? It's 1 times the chain rule, dp dt. All right, what's the derivative of 2L with respect to T? 2 times the chain rule, dl dt. Plus, similarly, the derivative of 2W is 2 times the chain rule, dw dt. This is your quote-unquote velocity equation. Or it's the rate equation. That's what we're really after, the rate equation. Okay, now go through and take inventory. Every variable is going to be accounted for except one. In order to evaluate an equation that has 5 unknowns, you need 4 of the 5. So I have 3 unknowns here. I have the rate of change of the length, the rate of change of the width, and the rate of change of the perimeter. Well, notice the rate of change of the perimeter is what I'm really after. And it's already solved for dp dt. That's great. So in order to evaluate it, the equation requires that I know dl dt and dw dt at that moment. Do I? Yeah, those were given to me. So now all we have to do is plug in. Anytime you're going from a variable equation to a numerical equation, you have to show that you're plugging in something. So the easiest way to do it is just to reference one of these moments in time. I'll choose L when L is 10. So you could say then when L equals 10, colon. And now we're going to plug in. Notice there isn't even an L and a W in the equation. That doesn't matter. What that just means is that the rate of change of the perimeter is not a function of the current length and width, but it still references that moment in time. So now I just plug in. I get dp dt equals 2 times dl dt, which I labeled as negative 2, plus 2 times dw dt, which I labeled as 3. And now if we simplify that, we get 6 minus 4, which is 2. And the units are always going to be, this is nice, units of P over units of T. Perimeter units per time unit. So that's going to be what per what? Inches per second. So on any final numeric answer with units, we put them on the final answer. Now we can even write a sentence, right? Like the Koldiam sentence, remember those? Referencing the moment in time first. We could say when the length of the rectangle is 10 inches, comma, the perimeter is whatting? Increasing, because it's a positive number, by 2 inches per per second. There you go. When the length of the rectangle is 10 inches, comma, the perimeter is increasing by 2 inches per seconds. Excellent. So that's really all there is to a related rate question. There's no justifying. It's just that. It's easy. There's one more part, though. We want to know at that same moment, we still have the same picture in our aforementioned math lab. We want to know how fast the area of the rectangle is changing at that moment. So on part B, give yourself a target. If we want to know how fast the area is changing, I'm going to call that dAdt. A for area this time, we haven't used A yet. Okay. dAdt, that's the rate of change of the area. So that's your target. So again, ultimately, you want to relate the rate of change of area to the rate of change of length and width. But before you can relate their rates, you have to relate their quantities. So in a rectangle, how do we relate the length and or the width to the area? You multiply them. Good. So A equals LW. This is your quote-unquote position equation. It gives you the instantaneous size of a side if you know the area in the other side. All right, we want the rate equation. So the next step is you take the derivative with respect to t. Oh, by the way, can we plug in the L equals 10 and W equals 6 before we take the derivative? No, if you do that, you're going to get, in this case, the area is 60. And that might be nice to know. At that moment, the area is 60. We want to know how fast it's changing. If you plug in and then take the derivative, you're always going to get what for the derivative? 0. So some people want to plug in before they take the derivative. No, we don't do that. If it's a quantity that changes throughout the life of the problem, you can't plug it in before you take the derivative. You have to plug it in after because it's a specific case at that moment in time. All right, so now we have the area in terms of 2 variables. That's fine. We'll just take the derivative, which not only will be implicit, but also what rule? The product rule. So the rate of change of A with respect to t on the left is just dAdt. And now we have the product rule. So the derivative of L is dL dt times W goes for the ride, plus L stands fast, times the derivative of W with respect to t, which is dW dt. Now, notice it is already solved for dAdt. That's what we want. That's great. If it weren't solved for dAdt, you could still plug in and then solve. But how many unknowns do I have on the right-hand side? Actually, I have 4, right? dL dt, W, L, and dW dt. Since I'm trying to find dAdt, I have to know all 4 of those at that moment in order to evaluate it. Do I? We do have all 4 of those, yeah. So let's go ahead and do the plug-in. Again, referencing the moment in time, I'll just say when L equals 10, we get dAdt equals dL dt, which was still -2, times W at the moment, which is 6, plus L at the moment, which is 10, times dW dt, which is +3. Now notice in both of these calculations, if you had given the wrong sign to either one of the rates, you're going to get the wrong answer, right? So like if you made them both positive, you're going to be adding them instead of subtracting one from the other. Sometimes you just get the opposite of the right answer, but a lot of times you're going to get the flat-out wrong answer. So that's why it's so important and why we started with it, to get the correct sign on your rates. From here, it's just a matter of simplifying. You get 30 minus 12, which is +18. And then what are the units? Inches squared per second. Yeah, inches squared per second. So now you can extend that sentence. When the length of the rectangle is 10 inches, comma, the perimeter is increasing by 2 inches per second, while the area is increasing by 18 square inches per second. You got it. Oh, okay. But you're not going to do that this year again. Yeah. Yeah. The only real mistake is making the same mistake twice. Yeah. Okay. Example 3. By the way, how'd y'all feel about example 2? Pretty easy? Kind of boring, I know, because it's just a rectangle. I don't know why you buy tickets to the 50-yard line to watch the rectangle change. Maybe there's nothing else to watch. But the method is the same for all problems. Example 3. A right triangle. Ooh, lots more interesting. A right triangle than a rectangle. This is a right triangle, guys. Whose sides are changing? Oh, they're changing. Great. The sides are 30 and 40 at a particular instance. When we say sides, that means legs. That means non-hypotenusal sides, okay? So 30, 40. Oh, wow, you're already all over that. if the shorter of these two sides is increasing by 3 inches per second, while the longer side is decreasing in 5 inches per second, how fast is the A, area, and B, hypotenuse changing? Man, I'm so excited I can't even calm down enough to know where to start. With a picture, maybe. Okay, let's draw a right triangle. And don't try to draw an isosceles right triangle. Draw kind of an atypical version where one is longer than the other. Okay? You're trying to draw it similar to what you might imagine it being at that snapshot moment. And it said that one side was longer than the other. Now, because these are all changing, you don't want to just label the short side as 30 and the long side as 40. Because now you're labeling those as constants. And are the sides constants? No, they're changing. So don't label that there. Instead, label it, I'll call it H and B. Why the heck not? Height and base. Now, in this case, the base is the longer of the two, the way I drew it. So I'll make my snapshot moment. When the B value that I'm calling B is 40. We can. That's not a bad thing. If you're going to get confused with H as the hypotenuse instead of the height, yeah, then call it A. I'll call it A. That's fine. So the snapshot moment is when B equals 40 and A equals 30. Now I'm going to leave a little bit of room in my camera, and I get very artistic here, right? When you hold the camera upside down, hold it, right, and the flash comes out the bottom. Fancy, your photographer there. So those are the snapshot moment values. I've already drawn my triangle. I've labeled the unknowns. Now it's time to decipher the rates and label them. The shorter of the two sides, which we're calling what? A, is increasing by 3 inches per second. So that's dA dt. And is it positive or negative? Positive 3. While the longer side, which we're calling B, so it doesn't matter if you call them A or B or B or A, but what matters is once you decide which one's the longer and shorter, now the rates matter. That one is decreasing by 5, so that's going to be negative 5. All right, so there's all the groundwork for the setup. That's all it's needed. Give yourself some variables, identify the snapshot moment, and write your rates mathematically with correct sign. All right, so now part A. We want to know how fast the area is changing. So again, I'll write that as dA dt equals question mark. It's our target. So I want to relate the rate of change of area to the two sides, but before I can relate their rates, I have to relate their quantities. So in this right triangle, the area is what? 1/2 base times height. Yeah, so for me, that's 1/2 AB. So the equation, that's the equation you're going to be differentiating, it usually comes from something geometric. So you kind of have to know your formulas for geometric shapes. All right, now that's in terms of two variables, which is fine. We're okay with that. That's your quote-unquote position equation. We want the rate equation now. So now we'll take the derivative with respect to t, and we get dA dt equals, and I'll use the product rule. I'll just associate the 1/2 with the a. So I get the derivative 1/2 a to be 1/2 dA dt times b goes for the ride, plus 1/2 a goes for the ride times dB dt. Since you're typically taking the derivative with respect to an equation that doesn't have any t's in it, every single variable should get a d variable dt. So don't forget them. All right, this one happens to also be solved for what I'm looking for, dA dt. So that means I have to know all four of the quantities on the right. Do I know dA dt at the moment? I do. Do I know b at the moment? Yes. Do I know a at the moment? Yes. Do I know dB dt at the moment? Yes. Okay, so I got them all. Sometimes you might be short one, and you have to go off to the side and kind of find it. And the way you typically find the missing quantity is by going back to the position equation, or doing something else, which we'll look at it when the time comes. All right, so now we just got to plug in. So I'll reference b, whatever. When b equals 40. When b equals 40, colon, we'll plug in. We get dA dt equals 1/2 times dA dt. So this is why you really want to clearly label everything. You're going to be plugging in a lot of things. And the fact that they're labeled, it makes them easier to just grab them off the shelf, you know. So 1/2 dA dt is 3 times B, which is 40, plus 1/2 A, which is 30, times dB dt, which is -5. Now that's a numeric answer, so if you decided to stop there, you would want to put units. That would be square inches per second. But we'll go ahead and simplify it. We're going to get 20 times 3 is 60, minus 45. No. We get 15 times 5, 75, minus 75. So that equals -15 square inches per second. So if you would write the sentence, the cold yam sentence, you would say, when the longer side is 40 inches, when the longer side is 40 inches, comma, the area is decreasing now by positive 15 square inches per second. Remember, if the rate is negative, you interpret that in the sentence as decreasing by the positive rate amounts. You're breaking the vector apart and listing the direction and the magnitude separately. You don't want to say it's decreasing by negative 15 inches squared. Okay, the numeric answer is negative 15 inches squared. All right, and then we also want to know at that moment how fast the hypotenuse is changing. So since Colin wanted to reserve h for hypotenuse instead of the height, I'll use h here. And on part B then, our target is dH dt. I want to know how fast the hypotenuse is changing. Well, gosh, man, before I can relate the rates, and by the way, I have the option now. I can relate the rate of change of the hypotenuse to either the rate of change of the area, since I have it, and or to the rate of change of either the two sides. Whatever is easier. Whatever equation you think is easier. I think it's easier to relate the sides in a right triangle to the hypotenuse, right? How do we do that? A squared plus B squared equals H squared. Yep. The theorem that the murderers gave us, the Pythagoreans. Remember the guy's name? You remember the punchline to the joke, right? As he's going over bypasses. Okay. Because his name was Hypassus. Hypassus. Yeah. Okay. Good story. We have, wow. Do we need to solve that for H or solve it for A or anything? You don't have to. No. We're interested in dH dt. If you want to solve it for H, go for it. You're going to have the square root on the right-hand side, and you're going to have to use an arduous chain rule. 1/2 blob to the negative 1/2 times. We're going to be taking the derivative implicitly anyway, right, with respect to time. So there's really no advantage necessarily to solving for H first, except that in your derivative you won't have an H. Not having an H value is not important to us, because if I know the A and the B value, I can find the H value. But I don't need to find it yet, so I'll just find it when I need it. All right, so here we go. D dt. The derivative of A squared with respect to t is 2A times the chain rule dA dt. Plus B squared is 2B dB dt. The rejected line in Hamlet. The derivative of H squared is 2H dH dt. That one was also rejected on more than one grounds. There's your rate equation. How many unknowns does it have in it? 6. So I got to know 5 of the 6 in order to evaluate it. Can we make it simpler? We could divide out the 2 from both sides. You want to do it that way? That's fine. Factor out the 2, it divides out from both sides. So we're just left with A dt plus B dB dt equals H dH dt. And we're looking for dH dt. You can solve it for dH dt as a literal equation, a formula, but I think it's just easier to plug in and then solve. Plug in and then solve. Things start combining a lot more quickly when you plug in. So now we have to reference the moment in time. When B equals 40, I'll stick with the same one. When B equals 40, that's the instantaneous calculus part of it. We got A is 30. All right, we got A is 30. dA dt, oh man, that was given. That's 3. Sweet. Cooking with oil right now. B is 40. Oh yeah, oh yeah. dB dt, that was given to be -5. Look at me go. That equals H times dH dt. So H is, I don't have H. Colin has it, but I don't have it. Colin has it. I don't have it. Maybe that's why I don't have it. Did you take it from me? If you would have solved for h first and got the square root of a squared plus b squared, you wouldn't need to know h. You would have Dhct equals. So that's the only advantage of solving for h, but it makes the derivative harder. All you have to do to find the missing value in this case is plug it back into your quote-unquote position equation. So when a is 30 and b is 40, by the Pythagorean theorem, h equals what, Colin? 50. Yeah, it's your 3, 4, 5 right triangle. So if you recognize it, that's fine. If not, you can actually go off to the side and do the math. 40 squared plus 30 squared equals h squared, and solve, and you get 50. Square root of 625. No. Sorry. 2,500. Sorry. 625 is different. Sorry. That's the old prefix for here in town. 625-4435 was my old phone number in high school. 625-4435. Call it now, I won't be there. Okay. You also have to dial the area code now, right? Now it's a what? 10-digit number? Anyway, I digress. Let's plug in. We know h now is 50. I was just nostalgic there for a moment. Pardon that. All right, so yeah. Are we done? We plugged in. Now we're done. Yeah, we got to solve for Dhct. So that's going to be as involved as dividing both sides by 50. So as I do that, I might as well simplify. I get 90 over here minus 200 over here, all divided by 50. Now, in a free response, you can walk away there, but I'm not on a free response. I'm training for both multiple choice and free response. So I'm going to keep going. I'm going to dare to keep going. That gives you negative 110 over 50, which is negative 11/5. And that looks good to me right there. So now I'll stop. And the units are units of h over units of t. Another advantage to Leibniz notation. If you somehow forget what you're doing, just look at the Leibniz notation. You have units of hypotenuse over time. That's going to be length units per time units, which is inches per second. So who wants to take the sentence? I'll start you off. When the larger side is 40 inches, comma, the hypotenuse, take it away. The hypotenuse is decreasing inches per second. Good. Yeah, excellent, excellent. So we're saying the sentence every time. We're not writing it out because it takes longer to write than to say it, but I might ask you on a quiz or a test to actually write it out. All right. Man, who knew you could have so much fun with shapes, rectangles, and triangles? Wow. Pretty impressive stuff. I could stop right now and just set you loose on the worksheet, and you'll be fine. Because you know the basic ideas behind a related rate problem. But maybe we should work an application together. Something that's less triangular or rectangular. Yeah. All right, if you want to read all this, this is kind of a summary of all the fun stuff we just did. But again, notice the key at the end is to smile if you're not already smiling all the way through. Just don't forget to smile. Okay. Example 4. An oil tank spills oil. You can stop right there. That's a fact. An oil tank spills oil. That's what they do. Right? They're designed to spill oil all over the ocean. This oiler is spilling oil that is conveniently spreading in a circular pattern, a series of concentric circular rings as it goes into the ocean, whose radius of the circular oil spill is increasing at a rate of 50 feet per minute. Ay, 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 look out, fishes. Okay, especially if you swim along the surface. How fast are both the circumference and the area of the spill increasing when, there's your snapshot moment, when the radius of the spill is 20 feet? All right, let's draw a picture of an oil spill. Yeah. So it's spilling out. I'm just going to do kind of, there's the center of the spill. It's emanating out, so I'm kind of using some of my Art 1 skills. Kind of perspective drawing there. It's supposed to be concentric, but we're off to the side looking at it. Okay, good. I know you're impressed. So I'm going to go ahead and just call this R. It's changing, right? It's changing. So immediately, if you want, since you called that R, it told us how fast the radius was changing with respect to time. That's going to be dr dt. And is it positive or negative 50? Positive. Man, wouldn't that be great if it was negative 50? That would be really great. Because then it would be like the oil spill is cleaning itself up. You should clean up after yourself, whether you're a person or an oil spill. You can't just rely on Kevin Costner to come do it all the time. What does that mean? Didn't we see the video in here with Kevin Costner? On the last BP oil spill, Kevin Costner had a machine that cleaned up the oil. Yeah. It basically pumped in the oily water and separated the water from the oil and pumped the water back and kept the oil. He made lots of money. It took him lots of money, and he had to convince Congress, but, he made lots of money. He cleaned up the oil spills. Way to go, Kevin Costner. Yes, the same Kevin Costner. That's the baseball actor. Okay, cool. So the RDT is 50. How fast are both? Okay, blah, 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 blah. I need a snapshot moment when the radius is 20 feet. So we're sitting there in a little boat, right? Hopefully outside of harm's way. We're right here outside of harm's way, and we're looking for Kevin Costner, and we have our little glitterati camera with us. And when the oil spill radius was 20 feet, we took a picture. So there's your snapshot moment when R is equal to 20 feet. Draw your camera. All right, so part A, it says how fast is the circumference. All right, so in part A, I'll call it A. I'll call the circumference C. So we're looking for dc dt. That's our target. So before I can relate the rate of change of circumference to the rate of change of the radius, I need to relate the quantities, circumference to radius in a cycle. So how do we do that? 2 pi r. Good. So again, it's another geometric formula. C equals 2 pi r. That's your quote-unquote position equation. Now you want the derivative with respect to time, so that's d dt. And you get dc dt equals 2 pi dr dt. And now you can plug in when r equals 20. Now notice this is the second time we've seen this. If you want to know how fast the linear quantity is changing, like circumference, notice it's not a function of the current size of the radius any more than the rectangle's perimeter was a function of the length and width. It's only a function of the rate of change. The two-dimensional quantities, like the area, those are a function of not only the rates, but the current sizes. But we'll still say when r equals 20, we get dc dt, which is what we're looking for. It's already solved for it, equals 2 pi times dr dt, which was 50. So we end up with 100 pi. And again, if that's where we're stopping, we put units of feet per minute. Now in part B, we want to know how fast the surface area. So I'll use A for area. So dA dt is our target. Now in the circle, I need to relate the area to the radius before I can relate their rates. Of course, that's what? A is pi r squared. Good. So there's your quote-unquote position equation. d dt, colon, of both sides. We get dA dt equals 2 pi r times dr dt. And now our snapshot moment when r is 20. You get dA dt, which is what we want, equals 2 times pi times 20 times dr dt, which is still 50. So notice this one is a function of both r and dr dt, and you end up with 2,000 pi square feet per minute. So if you're writing the sentence right now, you would say basically when the radius of the oil spill is 50 feet, the circumference is increasing by 100 pi feet per minute, while the area of the oil spill is increasing by 2,000 pi square feet per minute. And now the follow-up here. It says, if the depth of the oil, and people used to give me a hard time, oil floats on water. There's no depth. No, there is depth. Sorry, I was there. I should know. I didn't cause the oil spill, but I was there taking a picture for this problem. As the oil, if you look at it from the side, oil's pretty heavy, okay? So as it's glugging on here, it'll start to push itself underwater where the fish actually are. Look how little fish. Go the other way. He has a big tail. There we go. There's a fish. He's smiling. He looks like he did it, actually. That's a mischievous grin. The oil will start seeping down under its own weight, okay? So here's what we know. If the depth of the oil spill is given to be D of R equals 2R squared plus 1, that's convenient. That gives us the depth at any radius from the center. How fast is the volume of the oil spill changing? So let's go over here and put our target. I'll use V for volume this time. So dV dt. I need to relate the volume to either the radius or the depth or something like that. So here's how you do a problem like this. You can almost think of it as a circular prism, also known as a cylinder. If you know the area of the face, all you have to do to get the volume is multiply by the third dimension, which in this case I'm going to use D for depth instead of H for height. Because it's a regular surface, it's circular, times the third dimension. So the volume equation here is just pi r squared, right? That's the area of the surface, circular surface, times the depth, D, at any given value of r. All right, so now what is D? It's 2r squared plus 1. So thank goodness they gave it to me. I can actually plug it in, 2r squared plus 1. And now I have an equation for the volume of that particular oil spill whose depth is given by that in terms of the radius. I want to take the derivative, so I'm going to go ahead and distribute. That's going to be a 2 pi r to the fourth plus a pi r squared. That's your quote-unquote position equation. And now we'll take the derivative with respect to time. So we get 8 pi r cubed times the chain rule dr dt. Don't forget the d variable dt. Putting d dt every time will hopefully remind you of that. Plus 2 pi r to the first times dr dt. And now all you got to do is plug in. So it's the same thing. When r is 20, you get, oops, I forgot my left side. I forgot to put dV dt. I just went straight to the right side. So that's an honest mistake. If you find yourself that you've done that, just kind of come back and fix it. dV dt. There we go, and there's the right side. All right, so now it's solved for dV dt. That's nice. We just plug in very carefully. So here's where having everything off to the side labeled is easy. You could just kind of drop it right in. So you got 8 pi, r at the moment was 50, so that's 50 cubed. No, it's not. See, that's the RDT. I'm getting tunnel vision here and a bad memory. It's 20. Thank you. So r was 20. The RDT was the 50. And I'm running out of room, so let me slide this over a little bit. And then plus 2 pi times the radius, which now I remember is 20, times another dRdt, which is 50. And I'm going to let you simplify that if you want. That's great. I'm just going to call that a numeric answer. And if I stop there, then I need to put units. It's volume, so it's cubic feet, not inches, per minute. There you go. Without them giving you that depth, the depth was an irregular depth. It was like, polynomial depth. So it wasn't just like a uniform cylinder. It didn't sink down perfectly. It kind of sunk down at different rates. But they gave you the depth, and you will be given something like that. So you just kind of have to remember how to create a 3D model. It's the two-dimensional area times a third dimension depth. Okay? We'll stop right there. You got a good start on related rates. We'll start tomorrow with example 5, which is my favorite all-time related rate problem. Okay? You can see how much fun it's going to be. We'll explain that tomorrow. You thought the fish was smiling mischievously. Look at that guy.